Okay, so in lesson 4, we're going to take a break from talking about covalent bonds, and we're going to focus today on ionic bonds. But don't worry, we'll get back to covalent bonds in full force next week. So what we want to go over are some factors that will affect ionic bond strength and some of the characteristics of ionic bonds behind that. So let's do a little bit of a review about ionic bonds, first of all. So remember the ionic bonds, those are the type of bonds that we have in ionic compounds. And ionic compounds are really what they are is just a highly organized scaffold or 3D lattice of positive and negative ions. And these ions are just held together by attractive electrostatic forces. So for example, table salt, sodium chloride, it doesn't really have discrete molecules. Okay, they just have these ions and they're organized in a pattern like this. And this is just a section of the sodium chloride crystals that would obviously extend in all three dimensions, up and down, left and right, and in and out of the screen. Okay, but there's no discrete molecules when you have ionic compounds. There's no NaCl molecules. What you have is just this 3D lattice of positive ions and negative ions in a given ratio based on their charges. Whatever the charges, the ratio will establish such that the charges neutralize each other. Okay, one important thing to know about ionic bonds is they're generally stronger than covalent bonds, and we'll talk a little bit about why that is today. And how we measure that bond strength is with this parameter called the lattice energy. And to be more precise about it, it's really an enthalpy. And so it's given, it's indicated by the symbol delta H with the subscript LE for lattice energy. Okay, so let's talk about what lattice energy is. So the lattice energy can be defined as the energy that's required to separate 1 mole of the solid into its component gaseous ions, right? So we talked about how the bond energy would be, well, how much energy would I have to put into that carbon-carbon single bond in order to break it and separate the 2 carbon atoms? Well, that's essentially what you're doing here, but you're separating ions, and we're going to separate them into the gaseous ions. So an example of that would be taking solid sodium chloride and adding enough energy into it to convert it into free and independent gaseous sodium ions and chloride ions as well. So in terms of sodium chloride, that would require 788 kilojoules per mole. And so that number is an indicator of how strong those ionic bonds are in this particular compound. So the lattice energy, one thing about it is that it cannot be measured directly. You have to quantify it by combining several other known thermochemical parameters that we've already talked about in the course so far. So that's what we're going to do next, is talk about how we combine all these different thermochemical parameters to come up with this lattice energy. So really, it's an application of Hess's law, which we talked about back in week 3. We said that, hey, if there are some chemical reactions that I can't figure out the delta H of the reaction directly, well, maybe I can combine 2 or more known reactions such that they combine to form this unknown reaction, and therefore I can just combine their delta H's to get the delta H of this unknown reaction. So what we're going to do is really just an application of Hess's law, but it's given a very specific name. It's called the Born-Haber cycle, okay? So the Born-Haber cycle is just where we combine all the thermochemical steps that take pure elements in their standard states, and we take those to the gaseous ions. And then we're just going to compare that to the delta H of formation of that ionic compound. So we also talked about that back in week 3. Those delta H's of formation, remember, that's the energy change that occurs when we take elements in their standard state and we create the compound, 1 mole of the compound. What's the energy change when that is done? So we're going to utilize a lot of the things that we've already talked about this semester. All right, so let's just get into it, and we'll use the example of sodium chloride. So what steps must be taken to convert 1 mole of sodium in the solid phase and 1/2 of a mole of chlorine gas? Remember, chlorine exists as a diatomic gas, Cl2, in nature. And so we're going to convert that into sodium ions in the gaseous phase and chloride ions in the gaseous phase. Okay, so we're just going to kind of think through this and make a list, and then I'll show it to you in a picture. So the first thing, and that's another important aspect of this, is that, the reason why we're doing this is because all of these steps have already been figured out. Some smart scientist in the past did all this work and put these numbers in a table somewhere in some reference book. So all of these can just be looked up in tables, and we're going to just collect them and use them in this presentation. So step one, I know that what I need to do is I need to take solid sodium and I need to convert it into gaseous sodium, okay? And we remember we call that sublimation. That's something we learned back in week 1. All those phase changes, right? If I take a liquid and I convert it to a gas, that's vaporization, and then if I take a liquid and turn it into a solid, that's called freezing something, right? Well, this is just another phase change where I go from the solid phase directly to the gas phase. And so again, somebody figured out how much energy that requires and they put it in a table somewhere. And so, I've done you the favor of looking that up and putting it in our notes today already. So that requires 107 kilojoules per mole. So that's step one. Now, I don't want sodium atoms in the gaseous phase. I want sodium ions in the gaseous phase. So that's the next step. Step 2 is the ionization of those gaseous sodium atoms. Well, this is something that we've also talked about. We talked about this in week 4. We talked about a periodic trend of ionization energy, right? And so ionization energy was defined as how much energy is required to kick an electron out of the chemical species. That could be a neutral atom or it could be an ion. And in the case of sodium, going from sodium gaseous atoms to sodium +1 gaseous ions, that would be the first ionization energy. And again, you just look that up in a table and it's 496 kilojoules per mole. All right, so now I'm halfway there. I've gotten the sodium ions in the gaseous phase, so we can check that box. Now I want to focus on the chloride ions, starting with 1/2 mole of chlorine gas. So that's what I need to do is to take the chlorine gas, which is Cl2. So I've got that single bond between the two chlorines, and I just need to break that bond to give me 1 mole of chlorine atoms. So I'm just going to use 1/2 mole of the chlorine gas, right? I only need 1 mole of chlorine atoms, but 1 mole of chlorine gas has 2 chlorine atoms in it, right? Subscript 2. So I only need 1/2 mole of chlorine gas. And so again, what's the energy required to break that bond? This is something we talked about in lesson 3. We had it in the table, those bond dissociation energies, those bond energies for covalent bonds. So you look that number up in the table and it's 243, but I only need 1/2 mole of that. So I'm going to multiply that times 1/2 to give me 122. Okay, so now I've got chlorine atoms. Well, once again, I'm looking for chloride ions in the gaseous phase. I've got chlorine atoms in the gaseous phase. I need to convert those into chloride ions in the gaseous phase. So that is what we call the electron affinity. And this is a new term. It's not a new concept, but it's a new term. So the electron affinity is just defined as that energy change when 1 mole of the element adds 1 electron, or 1 mole of the substance adds 1 electron. Okay, so what's that energy change when that happens? Well, when you take chlorine atoms and you add a mole of electrons, or pardon me, when you take 1 mole of chlorine atoms and you add 1 mole of electrons to give you 1 mole of chloride ions, that's actually a favorable, energetically favorable process. So that's why this number is negative. You actually drop the energy. The chloride ions are lower in energy than the chlorine atoms and the electrons. So this product is lower in energy than these reactants. So you have energy released into the surroundings. So again, that should make sense because of what we learned back in week 4 when we talked about electronic structure. So when chlorine atoms grab an electron, they get their octet. They obtain that noble gas electron configuration. So it's a very favorable kind of process. So that's why, it's a negative number. Okay, so now we're good to go. We've got chloride ions and they are in the gaseous phase. And so now we have we have all of the numbers that we need to figure out the energy that it's going to cost us to go from the elements in their standard state to these ions in the gaseous phase. All right, so we just add up all those numbers, the 107, the 496, the 122, and we subtract 349. And when you do that, you get a net sum of 376 kilojoules per mole. Okay, so now the next thing that we do is we're just going to compare that total energy cost to create the gaseous ions to the known enthalpy of formation of the ionic compound. So again, remember what that means. So back in week 3, when we talked about the energy change going from elements in their standard state to the compound that had a value associated with it, the energy change of formation, the enthalpy change of formation. So that's known for sodium chloride. So we're just going to look that up and compare the two. And that difference, so when we take the difference between the two, that is the lattice energy. That's what we're looking for. All right, so we look it up and we see that the delta H of formation for sodium chloride is negative 411 kilojoules per mole. And again, that just comes from a table. And so I'm just going to take the difference between this total energy cost that I just determined in the previous slide and this negative 411 that I just looked up in the table. Okay, and so that lattice energy, that delta H of the lattice energy, is the difference between the two numbers. Okay, and that turns out to be 787. Well, that's, you know, due to rounding differences. Before we said there was 788. When we calculated 787, that's just a small rounding difference. Okay, but that is the lattice energy. So that is how much energy would be required to go from solid sodium chloride to the gaseous sodium ions and chloride ions. Okay, to separate those ions out of their crystal lattice and put them in the gaseous phase. It's the lattice energy. Okay, so all that's a lot of words, and hopefully it makes sense, but now I want to show it to you kind of in a picture. And so I'll talk through this a little bit, just to kind of recap what we did in the previous slides. So we started with our elements in their standard state, so sodium and chlorine. Okay, and the first thing I did was I figured out how much energy was going to be required to go from the sodium in its solid state to the sodium in its gaseous state. And that is the, you know, the delta H of sublimation, which was 107 kilojoules. Okay, but the chlorine didn't change. So we just kind of, you know, that goes unchanged from here to here. So now, and by the way, so this axis is meant to represent the energy. So the higher up we go, the higher the energy level. So then I have to add some more energy in order to go from sodium atoms in the gaseous phase to sodium +1 ions in the gaseous phase. And we call that the ionization energy, first ionization energy. So that is, you know, IE1. And that was 496 kilojoules. So I've already put in two significant amounts of energy to get to the sodium ions in the gaseous phase, okay? And once again, I didn't do anything to the chlorine, so that just moves up. So the chlorine, now what I've got to do is 1/2 of a mole of that chlorine, I'm going to break the chlorine-chlorine bond. So, you know, there's that chlorine-chlorine bond there, and I'm just going to break that bond. And so that costs me 122 kilojoules. And so all of those things cost me energy. So that's what brings me up to this energy level right here. Okay. And at this point, I've got sodium +1 ions in the gaseous phase, and I've got chlorine atoms in the gaseous phase. Well, I need chloride ions in the gaseous phase. Well, that is a process that's going to release some energy. So going from chlorine atoms to chloride ions releases 349 kilojoules per mole. All right, so that's what we dropped down in energy. But at that point, those are all the pieces and parts. Those are like all the pieces to the puzzle to get from elements in my standard state to the ions in their gaseous phase, right? Okay, so now I just compare that to the delta H of formation. There's a slightly different symbol here, so let me just redraw that. So that's the same thing as saying the delta H of formation of NaCl. Okay, so that, when I go from those elements to the compound, that is a energy releasing process, so a negative 411 kilojoules per mole, okay? And so then this brings me to this energy level with, if you look at that, you know, if you just go directly, remember Hess's law, so this would be the direct route, this is the indirect route, right? So if I remember right, that was 376. So once again, so going from here to here was 376 kilojoules per mole, okay? So that difference then, we got 376 here, and then you've got 411 here. That difference is, you know, the magnitude of that gap is 411. And so when I put those two numbers together, or you know, it's the same thing as taking the difference from one to the other, since this is a negative quantity, then that gives me the lattice energy. Okay, so this is a Born-Haber cycle example. Okay, so this is question number 65 in your extra practice assignment. I wanted to demonstrate how to solve this problem for two reasons. First of all, because it's just another example of the Born-Haber cycle type question. But also I wanted to illustrate a difference between the way that I teach this and the way that Chem 101 expects to see the answer. So we'll highlight that at the end. But what we're going to do here is we're just going to calculate the lattice energy, which, remember, that lattice energy we just talked about. It's the delta H of converting 1 mole of this solid into its component ions in the gaseous phase. So magnesium 2 plus in the gaseous phase plus 2 fluoride ions in the gaseous phase. All right, that's what we're going to do. So we'll start with, remember that the starting point is just the elements in their standard state. So I'm going to start with magnesium as a solid and a molecule of F2 gas. Okay, and we'll work on each one separately. So the first thing I need to do is I need to convert this magnesium solid into magnesium gas. All right, and so that is done with the process of sublimation. We're going to heat it up, sublime it, okay, and that's going to cost me 146 kilojoules per mole. So 146 kilojoules per mole. But the next thing I need to do is I need to convert these magnesium atoms into magnesium ions. And so I'll do that in 2 steps. So there'll be the first ionization energy, okay? And so that will create magnesium plus 1 in the gaseous phase. And so that's going to cost me 738 kilojoules per mole. But I also need to ionize it again into magnesium 2 plus in the gaseous phase. And that cost me 1,451 kilojoules per mole, okay? And so the fluorine hasn't changed at all yet. We're just kind of moving it along with us. But now, because I've gotten where I need to go with the magnesium, I have the magnesium ions. So all this energy is going to be required to convert a magnesium metal atoms in the solid phase to magnesium 2 plus ions in the gaseous phase. So now let's talk about what we need to do to this F2 molecule. I'm going to need both of them, so I don't need to multiply it by 1/2 like I did in the previous example. I need both those fluorines. And so what I need to do is to break that fluorine-fluorine bond. So there's that, that single bond connecting the 2 fluorines. So I need to break that bond. And so that is the bond association energy of F2. So that's 158. So that's going to be a plus 158 right there. So it gives me 2 fluorine atoms in the gaseous phase. So I'm going to kind of move this line over. So now what I need to do is I need to convert these fluorine atoms into fluoride ions, okay? So they're going to become fluoride ions in the gaseous phase, and that's going to drop my energy because of the octet rule and because of electron configurations, and that is how fluorine gets its noble gas electron configuration. So that's a stabilizing thing, that's a favorable thing, so it lowers the energy. And it happened twice. Each one of these fluorine atoms becomes a fluoride ion, and so that means I'm going to subtract 2 times the electron affinity for fluorine, which is 328, or pardon me, negative, well, the negative's right here. So negative 328 times 2. Okay? All right, so now I've got what I want. I've got 2 fluorides. I've got my magnesium, okay? So I've got both of the ions in the gaseous phase. Now, remember that there is another property that I need to take into account, and that is the delta H of formation of the compound, okay, magnesium fluoride, MgF2 in the solid phase. Okay, and so that is a process that lowers the energy. So I start with these elements, and when they form this compound, that's a drop in energy again, because these these products are more stable than these reactants, than these starting materials. So that goes down by 1124. Okay, and so what we have there is we have then a gap, and what I want to find is this gap right here, that gap right there. Because think about what the definition of lattice energy. The definition of lattice energy, according to the way that I teach it, is you're going from 1 mole of the solid ionic compound, and you're determining how much energy it takes to promote that, to separate those ions to the gaseous phase. Okay, so I take the solid ionic compound, how much energy do I have to add to break it apart into its component ions in the gaseous phase? So that whole gap there. So what I need to do is I need to do the math here, do all this math, and that will give me this number right here, that amount of energy right there. And then I just need to add that to the delta H of formation, and it will give me this gap right here. Okay, so let's do that. All right, so I've got the 146 plus 738 plus 1451 plus 158. And I'm going to subtract 2 times 328. Okay, and I get 1837. So right there, that's it. That is 1837. Okay, and so you know the difference here, or the magnitude of the amount. Remember, we took the difference. So 1837 minus a minus 1124. Okay, and that turns out to be 2961. Okay, so 2961 kilojoules per mole. All right, now, but before you put your answer in, let me tell you, Chem 101 wants this to be expressed as a negative number. And the reason why is because, I'll show you this when I show you the feedback. So let's just type it in. So negative 2961. Okay, and we'll hit view feedback and clear the screen. Okay, so it says we're correct, but here's the difference, and here's the reason why you have to express it as a negative number. It's because Chem 101, for whatever reason, defines lattice energy differently than I do when I teach it. They define it as the energy that is released when the gas phase ions become the solid crystalline ionic lattice. Okay, so they're going in the other direction. I define it in my lecture as the energy required to separate the component ions in the solid phase into their free and independent gaseous phase. But Chem 101 just defines it as just the opposite, the energy that's released whenever you take the gaseous ions and you form the solid crystal lattice. So just be aware of that. There is a homework question you have very similar to this, so just take that into account when you do the homework. Okay, so now what we want to talk about is we want to talk about factors that will influence the strength of these ionic bonds. And first of all, remember that the bond strength is indicated by the lattice energy. And so really, you know, what we can talk about are the things that influence the lattice energy. So there's a couple things that influence the lattice energy. First of all, it's the magnitude of charges. And the rule is, or the trend is, the higher the magnitude of charge, so the greater the magnitude of charge, the stronger the bond, or the higher the lattice energy, okay? So the greater the charge, the stronger the bond. That's one factor. And the other factor is the size of the ions. So once again, and this is very similar to what we talked about regarding the factors that influenced covalent bonds, right? When we talked about it with respect to covalent bonds, the closer the atoms were together, the stronger the covalent bond. Same thing here, but we have ions. So the closer the ions are together, which is determined by their size. So as we decrease the size, the ions are going to be closer together, and that's going to result in a stronger bond. So the size of the ions is a factor. As we decrease the size of the ions can scoot closer together, so therefore you end up with a stronger bond.
Yes, indeed.
So another indicator of ionic bond strength and lattice energy is melting point, something else that you can just look up for an ionic compound. And so we're going to talk about how these factors affect the melting point as well. Okay, so the strength of the ionic bond is also evident in the melting point. So the stronger the bond, the higher the melting point.
Ah.
Okay, stronger the bond, higher the melting point.
Ah.
Okay, so let's just do an example. We'll do a couple examples. So first of all, which compound would have the higher melting point, NaCl or magnesium sulfide? Well, let's think about the two factors that we just mentioned. So sodium ions, we know this is composed of Na+1, so that's got a +1 charge, and the chloride ions have a -1 charge. Well, magnesium sulfide, magnesium, those are going to be +2 ions, and the sulfides, those are going to be -2 ions. Okay, so the magnitude of charges are bigger on the magnesium sulfide. So I think that this one is going to have the higher melting point because this is different in that way. It has a higher magnitude of charge, so that means the lattice energy is going to be larger, and therefore it's going to have a higher melting point. Okay, so magnitude of charge on each of these. So all of these ions, oh, well, that's another important point, is that if you look at the periodic table, all of these elements are in the same period. So all of these ions come from the same period. So there's no significant difference in size. And therefore the distance is not significantly different. So that's not a factor here. But as we already said, the magnitude of charge is a factor. They're different. +1, -1, +2, -2. So magnesium sulfide should have the higher melting point. because it has the higher bond strength, because it has the greater magnitude of charge on its ions. Okay, so magnesium sulfide should have the higher melting point because it has the higher bond strength, because it has the higher, or because it has the greater magnitude of charge on its ions. You look at the melting points, you looked them up, you would see that is the case. Sodium chloride has a melting point of 801 degrees Celsius. Magnesium sulfide has a much higher melting point, 2000 degrees Celsius. So by the way, this is one way in which we can know that ionic bonds are generally stronger than covalent bonds, because compounds that engage in covalent bonds don't have melting points that are this high. They're much lower. The melting points of covalent compounds, molecular compounds, are much lower than these. So that's why we say that ionic compounds that ionic bonds are generally stronger than covalent bonds. Okay, so let's look at this next example here. So in this one, we are told to compare or predict the melting point of sodium chloride versus lithium fluoride. So once again, we can look at the magnitude charge. Well, we know that sodium is +1, chloride's -1, but lithium is also +1 and fluoride is also -1. So charge is not going to be a factor in this particular example. All right. So what we want to do is look at our periodic table and look at size. Okay, that's going to be the determining factor in this one. So the ion size. All right, so I'll let PowerPoint kind of take over from there to do that. So once again, the charges are all the same. The magnitude of charge is not going to be a factor because they are equal. +1, -1, +1, -1. So the magnitude of charges are equal. However, if you look at where these guys are in the periodic table, sodium and chloride come from period 3. Lithium and fluoride come from period 2. So the lithium fluoride ions are smaller and therefore closer together. So we can predict that lithium fluoride should have the higher melting point because it has the higher bond strength, because its ions are closer together than sodium chlorides. So once again, higher melting point because the higher bond strength or higher lattice energy, however you want to think about it, because the ions are closer together for lithium fluoride when compared to sodium chloride. Okay, so then you could prove it to yourself just by looking up the melting points. We already saw the melting point of sodium chloride was 801 in the previous example. And so if you look up the melting point of lithium fluoride, it is indeed higher, 845 degrees Celsius. Okay, so we'll stop there, and that ends the lessons that we have for this week. And so you just want to make sure that you get the homework done and the quiz done by Sunday, July 12th at 11:59. You should know enough now at this point to answer all those questions. And then here's a couple of good tutorial videos on the topics that we went over today.